Okay, so welcome to episode 10. In this episode, I'll talk about how to build an Arduino-based EEPROM programmer, and I'll cover a little bit why you might want to do this. We'll talk about interfacing an EEPROM, basically how you can make a CPU, or in this case, a microcontroller, talk to the EEPROM in order to read data from it, but more importantly, to store data in it. We'll cover the hardware design and also the firmware implementation. We'll talk about how to construct this circuit, including a sort of permanent version of the circuit like I have here. We'll talk about the development of the host software that allows you to actually sort of run on your PC a utility that allows you to burn data into an EEPROM device. And then we'll talk about whether or not this is a good idea. Okay, let's get started. All right, so why do we care about EEPROMs? Well, very simply, we need firmware in our 8-bit computer. That's the built-in code that executes when the system boots up. Definitely need that. EEPROM devices are a very good way to build that in. EEPROM devices, unlike other types of programmable memory devices, can be programmed without using special programming voltages. So if you have a UV erasable EEPROM like this thing, they typically require weird voltages like 12 volts or 21 volts. They're a bit hard to generate. EEPROMs can be programmed using 5-volt logic, just normal logic, so that makes them pretty easy to work with. And in general, they're not very expensive. They're easy to find. You can probably get them for like a couple of bucks each, so they're a good choice. The real question here is, why would you want to build your own programmer? The main thing you have to think about is that a dedicated device programmer, like this MiniPro TL866, they are both cheap, so you can get them for like, 50, 60 bucks. They're also amazingly useful. They can program all kinds of different devices. They're easy to work with. They're just generally useful to have. So from a purely economic standpoint, building your own programmer that can only program, these like EEPROM devices is, might not make a whole lot of sense. However, building things is fun. We'll learn some stuff by doing this. And one economic argument potentially is that if you can build your EEPROM programmer using parts that you already have, that you can pull from your junk box, you might be able to do this for only a few bucks. So let's talk about how EEPROMs work and how we interface with them. And here's a very simplified block diagram showing a 28C256 EEPROM device and then a system that is interfaced with it, which could be either our 8-bit computer, but in this case it's going to be our dedicated EEPROM programmer. So the idea is that the system sends addresses to the EEPROM device to tell it which byte of memory the system wants to access, and for a 32K EEPROM there are going to be 15 address lines, A0 through A14. There is an 8-bit bidirectional data bus that allows the system to send values to the EEPROM when it wants to write data, and then of course is also used for the EEPROM to send data back to the system when a byte is read. And then there are control signals. There is the CE signal, that is the chip enable signal, when the system asserts that, and note that it is an active low signal. To assert an active low signal, the system drives it low. When CE is asserted, that sort of wakes up the EEPROM and tells the EEPROM that the system wants to talk to it. There is the OE, output enable signal, and when the system asserts this signal, the EEPROM will send the data of the byte that is being accessed as specified by the address lines back to the system. So that's how the system reads data from the EEPROM device. And then the WE signal, write enable, when that is asserted, that tells the EEPROM that the system wants to write data to it. So whatever byte of data is being written by the system onto the data bus is then latched into the internal storage within the EEPROM device. And when these control signals are generated, there are certain timing characteristics that have to be followed. So let's talk about those. All right, so here we are looking at the datasheet for the Atmel 28C256, and here these are the characteristics for reading data and the waveforms for how to read a byte of data from the device. And the idea is pretty straightforward. This is pretty characteristic of these parallel memory devices that these old 8-bit systems use. that basically what the host system should do if it wants to read is first assert the address of the data that it wants to access, and then assert the chip enable and output enable signals, and then some period of time later, the memory device, in this case the EEPROM, will output the requested data on the data bus. And the most important timing characteristic here is the access time, which is the amount of time between when the address is asserted and when the data actually appears. And depending on the speed grade of the device, for a fast device that could be 150 nanoseconds, for a more typical device that might be 200 nanoseconds. That is plenty fast for these old 8-bit systems where, you could probably even wait, 500 nanoseconds and you'd still meet the timing deadline for the host CPU. All right, so next let's talk about writing data to an EEPROM. And before we talk about the specific control signals and timing requirements required to write data to the EEPROM, there's one important thing we need to mention about how writes to EEPROMs work, which is that after the appropriate control signals have been generated to request that data be written, it takes some time for the EEPROM device to actually commit that data to the EEPROM's internal storage. And until that internal write cycle completes, we can't actually do any other useful reads or writes. And that's sort of hinted here in the datasheet. Once the end of a write cycle has been detected, a new access for a read or write can begin. So in other words, if we wanted to do a series of writes, writing to a number of locations, and of course this is typically what we want to do when we program an EEPROM, we want to basically write to all of the internal storage to the device. This write cycle timing is going to potentially limit the throughput of the data, kind of how fast we can write data to the device. And what's important is that it takes a good amount of time for that internal write cycle to complete. The datasheet here says 10 milliseconds, and 10 milliseconds doesn't sound like a ton, but as we'll see, if we write 1 byte at a time, that's actually quite slow. So to see why this write cycle time is potentially a problem, let's think about what would happen if we wrote to every single storage location in a 32K EEPROM device 1 byte at a time. So in a 32K EEPROM, there are 2 to the 15 byte-sized storage locations, 32,768. And if we consider that each one of these storage locations would take 10 milliseconds to write to, that's more than 327 seconds, or in other words, about 5.5 minutes to write to every single location in that EEPROM device. So the good news is that there is a way that we could avoid incurring this delay for every single byte. So next, let's talk about the specific programming waveforms we need to generate to write data to an EEPROM device. All right, so let's talk about how to write 1 byte of data to an EEPROM. And it's sort of what you might expect. The idea is that the host CPU or microcontroller asserts the address of the data that it wants to write. It asserts the chip enable signal to wake the EEPROM up. And then the write itself is controlled by the write enable signal when that is asserted by being sent low. That essentially tells the EEPROM that a write has been initiated. The data needs to be asserted onto the data bus during this time when the write enable signal is low. When the write enable signal is deasserted, being brought high, that is essentially the point where the EEPROM understands that, okay, the data has been sent, and whatever data was read from the data bus should be committed to the internal storage. There's a couple of timing characteristics that we have to satisfy here. There is the TWP characteristic, which is the write pulse width. That needs to be at least 100 nanoseconds, so we have to make sure that we hold the write enable signal low for at least 100 nanoseconds. The other one is this TWPH, that is the write pulse width high, which needs to be at least 50 nanoseconds. And essentially what that means is that after the write enable signal is deasserted, we have to wait at least that long, meaning at least 50 nanoseconds before we attempt to write more data by sending the write enable signal low again. All right, so now that we know how to do 1-byte writes, now next let's look at how to do page mode writes. And page mode is essentially the bulk data transfer mechanism that allows us to write larger quantities of data quickly, because we won't have to incur that internal write cycle timer for every single byte of data that we write. And the good news is that page mode writes are actually quite similar to single byte writes. We assert an address, we assert the chip enable, we assert the write enable, we meet the minimum write pulse width, we make sure that the write enable signal is deasserted for at least the write pulse high time. That's all the same as before. We sort of assert and deassert the chip enable as appropriate for each byte of data. What makes a page mode write is that we leave the write enable deasserted for at most this timing characteristic called TBLC, byte load cycle time, and that is 150 microseconds. So the way to look at it is, as long as write number 2 happens no more than 150 microseconds after write number 1, they are both considered to be part of the same page mode write. And we can do up to 64 writes as part of a single block of page mode writes. There's restriction. They all have to be in the same block of addresses starting on a multiple of 64. You can only write to the bytes within a single page of the EEPROM's storage. That's why it's called the page mode write. But as long as all of those writes occur in the same page and that they're all no more than 150 microseconds apart, they all get written essentially as a block, and you only incur that internal write timer once. So that means that, aside from the amount of time it takes to actually sort of do all of the writes in a page, which is relatively quick because we're talking about, nanoseconds and microseconds here, we only incur that longer 10 millisecond delay one time per page. All right, so now that we've talked about how to interface with an EEPROM device, let's talk about what we need in our hardware for our programmer. And we are going to make the brains of the operation an Arduino Nano. So you almost certainly have heard of Arduinos. They are just an amazing microcontroller family that are designed to be easy to use and just really, really fun and just productive, I would say, is maybe the way to look at them. We are specifically going to use the Arduino Nano. These are based on the ATmega 328 or potentially ATmega 168 chips. What's really awesome about Arduino Nanos is that they're really, really cheap. You can get them for like $2 or $3. Like these blue ones are, maybe $2.50. I got these red ones that are based on the 168 for less than $2 each. It's incredible. They appear to the host PC as a USB serial device because they have a USB serial converter chip on them, meaning you can have your host PC talk to your firmware program running on the Arduino via essentially as a USB serial port. And so that's how our host software for the EEPROM programmer is going to talk to the microcontroller over USB serial, so that's fantastically useful. Arduino Nanos have 15 digital I/O pins, basically pins that can send arbitrary digital output signals or read arbitrary digital input. They have 8 analog inputs, and these are based on analog to digital converters. 6 of the analog inputs can actually be digital I/O pins. So that means you've got a total of essentially 21 digital I/O pins available, so you can interface to all kinds of stuff. It's really awesome. And what's really, really great about Arduinos is that there is an incredible ecosystem of libraries for easily interfacing your Arduino firmware to all kinds of useful peripheral devices. Like, this is the real magic of the Arduino ecosystem. All right, so to control our EEPROM device, we need to be able to generate 15 address signals. We need to be able to read and write 8 digital data lines, and then we also need to generate outputs for the 3 control signals that feed into the EEPROM. And so if you're counting, that's 26 digital I/O pins that we would need. Our Arduino Nano only has 21. Okay, so how are we going to make that work? All right, so the way we are going to get around the limited number of I/O pins we have available on our Arduino is to use shift registers. And essentially what shift registers do is allow you to take a small number of I/O pins on your microcontroller, 3 or 4 is typical, and use them to control multiple outputs or read from multiple inputs. And the specific shift registers that we're going to be using are the 74HC595. That is a output shift register. It has a single serial input, and so if we send it serial data, it will decode that and generate 8 digital outputs. We will also be using the 74HCT165, which is an input shift register, so it has 8 digital inputs that it will then encode onto a single serial output, which we can then read and essentially read the encoded form of the data values read on those 8 digital inputs. And one additional feature of shift registers that you can take advantage is that due to the way they work, they can be typically can be daisy chained together in order to create larger shift registers. So, for example, we're going to combine two 74HC595 shift registers to generate the address outputs to control to basically tell the EEPROM the address of the data values that we want to access. Okay, so in our hardware design, we're going to use 2 595 shift registers for generating addresses. We're going to use one 595 shift register for writing data values to the data bus that the EEPROM will then read. When we're writing data to the EEPROM, and then we'll use one 165 shift register for reading data. Basically, when the EEPROM device outputs data to the data bus, we can use that 165 shift register to read it. Okay, and this is not going to be a tutorial on how to use shift registers. This video is going to be long enough anyway, so read up on them. They are really, really useful in cases where you need to expand the digital I/O capacities of your system or perhaps a microcontroller. All right, so here is our hardware schematic. So here's the Arduino Nano. Basically, we're just connecting the digital I/O pins to the control pins on our shift registers. That's pretty much how we've interfaced the Arduino to the system. A couple of the digital I/O pins are used to control some LEDs that indicate what the data direction is, basically whether the programmer is reading data or writing data. We have 2 cascaded 595 shift registers here that generate addresses. So we'll send 16-bit addresses to these 2 shift registers, and they output the signals that are then fed into the address lines on the EEPROM. This particular 595 shift register is used to generate data. So we send it 8 bits, and it can output those that 8-bit quantity onto the data lines that feed into the EEPROM. One very important thing we have to do for this shift register is make sure that we are sending a control signal to the shift register's output enable input because basically we need to be able to disable the output of the shift register when we aren't writing data. Because if we are reading data and the EEPROM device is trying to output to the data bus, we definitely don't want the shift register trying to also output to the data bus. Let's see. So this is our input shift register, the 74HCT165. That's also connected to the data bus. And when we give the instruction to the shift register to read that data, it then allows us to sort of read out the data that was observed on the data bus and send it back to the microcontroller via a serial input. And then this is the actual EEPROM device itself, which typically will be a 28C256 EEPROM, but could be a 28C64 EEPROM. That's an 8K device. Essentially, that has the same pinout as the 28C256. It just ignores the 2 highest address lines. Meaning as long as you're only writing 8K of data, you can basically treat that device exactly the same way as the larger device. All right, so here is our circuit on the breadboard, the Arduino, the 2 shift registers that generate addresses, the shift register that writes data values to the EEPROM, and the input shift register that allows us to read data values from the EEPROM, and we have a ZIF socket that allows insertion and removal of the EEPROM device. That's certainly something that you'll want to have in your programmer. Not a whole lot to say about this particular version of the circuit, other than that it is exactly the same as what's in the schematic, and this is how I developed my firmware is by burning the firmware onto the Arduino and then testing things to see if they worked. All right, so here is the production version of the circuit, if you will. I built it on a proto board, one of these, and the kind of proto boards I think make a lot of sense if you're building a permanent version of a circuit are the ones that essentially have sort of a breadboard type arrangement of pads on the bottom. You can see there are these groups of 4 holes that are connected by a common copper pad, and so if you basically put wires into holes that are part of the same group, then you've created an electrical connection between them. It's essentially the same arrangement as in a solderless breadboard. And so if you look at the back of my constructed circuit here, you can see that all of these, wires and components, that are on the top of the board, and have sort of wires going between them. I have soldered all of those pins and wires in the appropriate locations on the back, and essentially it's the same idea as constructing the circuit on a breadboard. It's just that you are permanently soldering the ends of the wires and the pins, into the circuit. I have used sockets for all of the shift registers. I think that's a good idea just because, if you fry a chip, you can just pop it out and put another one in. As I was constructing the circuit, I spent a lot of time with the multimeter and continuity mode, checking connections and making sure that they exactly match the schematics. And, as you can see, there's a lot of wires. It took a little bit of doing to kind of figure out a good way to run all of the wires so that there would be enough space to access the components and stuff, but it did all work out. I do have a ZIF socket soldered in here. The pins on the ZIF socket are actually too big to fit through the holes in the proto board, so I soldered header pins onto them that were smaller, and then those did fit in, so it is permanently attached. I have also very amateurishly cut some Lexan to serve as kind of a rigid enclosure, and you can see there's 2 sheets of Lexan and then some standoffs, and just to kind of protect the electronic components. All right, so now let's talk about the firmware. So this is essentially the firmware program that's running on the Arduino microcontroller, and it, of course, is the brains of the operation. It basically has 2 responsibilities. One is to generate the control signals that are sent to the EEPROM device via the shift registers in order to write data and read data. And then, of course, the other responsibility is to interact with the host system, either sort of directly, interactively, or via our specialized host program utility that I'll show you a little bit later. So let's start by looking at the setup function. And so the setup function in an Arduino program essentially just does the one-time hardware initialization to get the system into an appropriate initial state. So it sets the data direction for the various I/O pins that are being used, and then performs other important hardware initialization. And then the loop function runs again and again and essentially forms the basis of the program's main control loop. What the EEPROM programmer firmware does in its loop function is to print a prompt and then wait for a command, and then it carries out the command by calling the appropriate command function. So let me demonstrate how we interact with the firmware. When you are developing Arduino firmware that uses the serial connection to interact with a user or interact with some other piece of software, one of the really cool things about the Arduino IDE is it includes this built-in serial monitor that allows you to just interactively send data to the Arduino, and it will print out the data that is sent back. And as long as you use kind of a text-based protocol for interacting with the device, this is a great way to sort of interactively develop and debug your firmware program. Okay, so let's see. So I'll send a question mark command. That just causes the firmware to print out some version information, and it also reports what the current address that the firmware is accessing is. Okay, so let's set the address to 1000. In hex, that is represents the decimal value 4096. Okay, and now if I read 16 byte. So the R command is for reading data, and 10 is the hexadecimal representation of 16. It's going to show me the exact 16 bytes of data that are at that address. Okay, so now let's try to write some data. So I'm going to set our address back to 1000 hex, and I'm going to write the data value C6. This is just a 1 byte write, and so in theory that should change the data at address 1000 to C6. So let's see if that actually worked. So I'm going to set the address back and then read 16 bytes. And what we notice is that the byte of data at that address didn't actually change. And the reason it didn't change is that EEPROM devices actually have a hardware write protect feature, and if that write protect feature is enabled, you can't actually write data to the EEPROM. So I have implemented support for both enabling and also disabling the hardware write protection. So the firmware's D command disables write protection, and write protection is turned on and off by sending a particular sequence of data writes to a particular sequence of addresses. You can read about it in the data sheet. All right, so now that write protection is disabled, I'm going to go back to address 1000, and let's try to write the value C6 at that address again, and then see if that write actually took effect this time, and there it is. So we have written 1 byte of data to our EEPROM. All right, so as we saw, writing 1 byte of data at a time is slow due to the write cycle timer. So what we want to do is use the page mode to write up to 64 bytes at a time, and the firmware does support page writes via the P command, and the format of the command is that it's P, and then it's the count of how much data you're sending. I'm going to send 8 bytes of data, and I'm just going to write the bytes 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8 as the hexadecimal values that are going to be written. I'm writing those at address 1000 again. So now if we read some data from that address again, I'll read 16 bytes, right? We now see those exact bytes of data at that location in memory. And because this page write allows us to write 64 bytes at a time, but only incur the write cycle timer delay 1 time for all those 64 bytes, that gives us a reasonable amount of throughput, and this is very important when we are, for example, writing the entire contents of the EEPROM. All right, so in general, developing the firmware was reasonably straightforward. I was able to kind of interactively, update the firmware and test it and, verify that things were working. And I was able to, read bytes of data and write single bytes of data. All that was fine. The one problem I ran into is when I tried to implement support for disabling the hardware write protection feature, I found that even if I wrote the correct special sequence of data values to the special sequence of addresses, as described in the data sheet, I just couldn't get the write protection to actually turn off. And what I found eventually is that the timing requirements for that special sequence of data writes needed to conform to the same timing characteristics as for page mode writes. And specifically, the problem I was running into was that I was not meeting the byte load cycle time requirement, that the writes that were part of the same sequence couldn't be more than 150 microseconds from each other. The reason I wasn't able to meet that timing deadline was that the code that I wrote to communicate with the output shift registers in order to kind of get the data sent to the EEPROM, I was using the Arduino's digital write function, which essentially just says, given a certain pin, set it to a certain value, high or low. The digital write function for Arduino is very easy to use, but it is quite slow. And in fact, it is so slow that I just wasn't able to, get all of the signals sent in 150 microseconds. And so the way I fixed the problem was to change my code to directly access the underlying hardware registers that the AVR AT Mega 328 microcontroller uses to directly control those I/O pins. And once I made those changes, I was able to meet the timing requirements. So that's something to be aware of with Arduino, is that some of the convenience features like the digital write function may not perform well enough if you are having to meet very precise timing requirements. But once I made that code modification, I was able to enable and disable write protection with no problem, and then that also allowed me to easily implement the page mode write feature, and so at that point things were good. All right, so now let's talk about the host program. So this is the program that runs on the host PC that allows you to, burn data to the EEPROM or read data from an EEPROM and, disable write protection, enable write protection, that kind of stuff. And there's not a whole lot to say about it, in the sense that essentially all it's doing is just automating the process of sending commands to the EEPROM programmer and then reading the responses back, such as data read from the EEPROM, and just kind of driving whatever it is that the user wants to do. And here's the main routine. It just checks command line arguments and then calls various functions to write data to the programmer or read data from the programmer. I think what would probably be more interesting is to sort of demo it and just kind of give you a sense of how it fits into the workflow. So here I am in the code directory for episode 9, and I'm going to assemble our blink.bin program that controls that little 7-segment display. And of course the blink.bin is a 32K 6809 code image that we want to program into the EEPROM. The host program is called EEPROG. So if we issue the command EEPROG-H, that prints a little usage message and tells you what the command line arguments are. What we're going to do is the full command is we are going to use the -f command to specify the firmware file that we want to write. The -p option allows us to specify the device name for the serial port. So right now my Arduino is /dev/tty USB 0. It's pretty typical. The -D disables write protection. -N will re-enable write protection after the data write has been completed, and then the -V causes the utility to verify that all the data was written correctly, but basically by reading the data after all the data has been written. Okay, so let's see if that works. Okay, so the host utility is now talking to the firmware, and it's writing the data. Each of these dots that are being printed as a progress indication indicate 1K of data. So it's going along at kind of a reasonable clip here. Certainly it's not going to be anything like the 5 minutes that would be required if we were doing 1 byte at a time. So the write has now in theory completed, so now it's reading the data back in order to verify that all the data was written correctly, and essentially the host program just checks the data buffer where the data was read and verifies that it is byte for byte identical to the data written, and if so, then we should be in good shape because our data is now in the EEPROM. All right, so to conclude, let's think a little bit about whether or not this project was worthwhile. So I will definitely acknowledge there was significant time and effort involved. It took some time to design the hardware, to construct the hardware. Soldering all those wires definitely took some effort. The development of the firmware and the host program took some time. So that's definitely something to consider. As far as the cash expenses, they weren't too bad. I had most of the parts I needed on hand. I did spend maybe $20 or so to get those Lexan sheets to build the enclosure and also the standoffs that I used in the enclosure, although some of those were left over and I'll use those in future projects. The real reason to do this kind of project is as a learning experience. So one of the things I thought was interesting was the way I figured out that problem with the timing of page writes was I actually got out the oscilloscope and monitored the write enable signal on the EEPROM, and it was extremely obvious from looking at the traces on the scope that those write pulses were more than 150 microseconds apart, and that definitely told me what the problem was and gave me a head start on figuring out how to solve it. And just in general, I think it's good to follow through on these projects and really see them to completion, and just the experience of diagnosing problems and figuring out a solution kind of helps you be more productive in getting other projects done. Okay, and as always, you can look in the video description and there will be links to the schematics in the code. Definitely feel free to use them however you see fit. And in the next video, we'll return to the 6809 system and definitely add some RAM, maybe add some peripheral devices. So I will see you in the next video.